wanted to spend some time solving some trigonometric equations with you. And here are the directions that we're going to use. Solve each equation for solutions in the specified interval. When possible, state exact solutions, and otherwise state solutions to the nearest hundredth. So we're going to be using our calculator. But let me first be clear here. I did this for simplicity. When possible, state exact solutions. Honestly, you could always state exact solutions. By this I mean, if the angles have reference angles that are our special angles, we should be able to say them exactly. Or if the solutions are quadrantal angles, we should state them exactly. Otherwise, we're going to grab our calculator and find solutions to the nearest hundredth. So when possible, state exact solutions, I'm talking about special angles and quadrantal angles. And I'll make that point one more time on the first example. Okay, so let's go. The first problem we're going to solve is this one. It will be to solve for x if x is in the interval 2 pi to 4 pi. Often we solve between 0 and 2 pi, but I just want us to practice a different kind, right? So here's the equation we're going to solve. We're going to solve 9 sine x plus 1 equals -4. And we're going to solve for that in the interval 2 pi to 4 pi. So let's solve for sine of x first. So we have 9 sine x equals -5. Divide by 9, and we have the sine of x equals -5/9. And now we grab our calculator so we can find our reference angle or reference number since it's in radians. So when we punch an inverse sine, I'm going to put it in with a +5/9 so that the reference number or reference angle will be displayed on my calculator. I get 0.59. So there's our reference number. So we want the solutions in the third and fourth quadrants because our ratio is negative. But we want our solutions between 2 pi and 4 pi. So if we're between 2 pi and 4 pi, that means we've gone all the way around and we're coming over here to the third quadrant. So we've gone around to 2 pi, and then over here we're at 3 pi. And if you continued on, you'd be at 4 pi. So our solution is going to be 3 pi plus 0.59. And it's going to be 4 pi minus 0.59. So that we would have the solutions in this interval. So let's use our calculators to get those. So we have 0.59. So if I take 3 times pi and add 0.59 to it, I get about 10 point, I'm putting approximately equal to here, just to remind you this is the approximation, 10.01. And similarly, if I take 4 pi and subtract 0.59, I end up with 11.98. Let me just double check that one. 4 pi minus 0.59. Yes, 11.98. So those are the solutions. And this is the part I was talking about, state solutions to the nearest hundredth. So that's what I want us to practice. Now, I mentioned that all solutions really could be written as exact values. So let me be clear. Right here, if you wanted, you could write it this way. 3 pi plus the inverse sine of 5/9. That was our 0.59. And the second solution is 4 pi minus the inverse sine of 5/9. So technically speaking, all of our solutions could be written in exact form, but I want to practice getting decimal approximations if they aren't special angles or quadrantal angles. Let's keep going. For our next equation, let's solve for x in the interval 0 to 2 pi. So just within that first rotation. And we're going to solve a multiple angle trig equation this time. We're going to solve cosine of 4x equals 1 over the square root of 2. And there are a couple of different ways to solve it. I'm just going to do it one way. I'm going to do this by making a substitution and considering this equation first. Cosine of u equals 1. Let me write that again so it looks better. Cosine of u equals 1 over the square root of 2. So I'm making a substitution for 4x. I'm going to let u equal 4x, just so my equation looks a little bit simpler. So now, if we solve for u, I know that the reference angle for this would be pi over 4. But we know the cosine is positive in the first and fourth quadrants. So u would actually equal pi over 4 or 7 pi over 4. But if x is in the interval 0 to 2 pi, we know we're going to have to go out further for u. U, we know, is going to need to be between 0 and 8 pi. So that when we divide by 4, because ultimately we're going to need to divide by 4, we'll have x's between 0 and 2 pi. So that means I'm going to go 4 full rotations. This is the first rotation. Let's continue. I'm going to think of the angles that are coterminal with pi over 4. So I'm going to add 2 pi. And when I'm adding 2 pi, I'm thinking of it as adding 8 pi over 4. So that would give me 9 pi over 4. Similarly, I would add 8 pi over 4 here. And now I've gone 2 complete rotations. I'm up to 4 pi. Let's keep going. We're going to add 8 pi over 4 again. And again. And we're going to add 8 pi again. And one last time. And what is that? 31 pi over 4. So now our u values are all the way out to 8 pi. And we need that to be the case because u is actually 4x. So let's put x back in. That means 4x equals pi over 4, 7 pi over 4, 9 pi over 4, 15 pi over 4, 17 pi over 4, 23 pi over 4, 25 pi over 4, and 31 pi over 4. And now to finish solving for x, we're going to divide by 4, or think of that as multiplying by a fourth. So our solutions are pi over 16, 7 pi over 16, 9 pi over 16, 15 pi over 16, 17 pi over 16, 23 pi over 16, 25 pi over 16, and last 31 pi over 16. And notice this is just under 2 pi because 2 pi would be 32 pi over 16. And we have our solutions between 0 and 2 pi for this particular equation. Let's do another one. Let me put a different piece of paper up here. Let's solve this one. So, and we're going to solve if x is in the interval 0 to 2 pi. And we're going to solve within that interval for each of the next problems we're going to do, for each of the 3 remaining problems. So we have this time 4 secant x plus 1 equals negative 10. So let's solve for the secant of x. We're going to subtract 1 and divide by 4. And I prefer to think in terms of the cosine since I have a cosine button on my calculator. So I'm going to take the reciprocal of the left-hand side and we'll have cosine of x. Take the reciprocal of the right-hand side and we have negative 4/11. Now here's the part where you need to be careful. You need to know what your calculator is giving you. If you punch in the inverse cosine, because I have people do this and there's nothing wrong with this, but if you let x equal the inverse cosine of negative 4/11, this will be a second quadrant angle. Remember, the inverse cosine of a negative ratio is a second quadrant angle. So that won't be the reference angle. A reference angle is positive and acute. So you could interpret it and use it if you wanted to, but I generally punch it into my calculator with a positive ratio. And if I do that, then I will get the reference angle. So I'm going to do that right now. Inverse cosine, positive 4/11. So if you punch that in, you'll have 1.20. But now I know I need solutions in the second and third quadrants because that's where the cosine is negative. So that means I'm coming over here to the second quadrant and I'm going to subtract 1.20 from pi. And I'm going to come to the third quadrant and I'm going to add 1.20 to pi. So if we do that, we would find our solutions are, and I just wrote equal, we know these are approximately equal to pi minus 1.20 gives us 1.94, and pi plus 1.20 gives us 4.34. And by the way, if you were to punch in inverse cosine negative 4/11, it would actually give you this 1.94. This angle right here is the inverse cosine of negative 4/11. But I have found many times people don't pay attention and recognize that this number 1.94 in radians is actually a second quadrant angle. Let's solve another equation. The next one we'll do is this one. And we're going to solve for x in the interval 0 to 2 pi. And here's the equation. 3 cosecant squared x plus 2 cotangent x equals 8. And I wanted you to see that we have 2 different functions in this equation, but we have some trig identities that allow us to make some substitutions so that we could get the equation written with respect to one trig function. That's not always required. Sometimes you could set an equation equal to 0, and if you could factor, even though there were multiple trig equations in the, or trig functions in the equation, that might be fine. But for this one, we're going to want to make a substitution. And remember, we have a trig identity that relates the cotangent and the cosecant. It's one of our Pythagorean identities. It's the one that says 1 plus cotangent squared x equals cosecant squared x. That's our relationship that we need for this particular problem. So we can just replace this cosecant squared with this. So let's make that substitution. And then if we distribute, we have 3 plus 3 cotangent squared x plus 2 cotangent x equals 8. And let's set this equal to 0 and rearrange. I'm going to put the 3 over here, subtract the 8, so our equation would become this. 3 cotangent squared x plus 2 cotangent x minus 5 equals 0. And now we have it quadratic with respect to the cotangent of x. Really, it's quadratic in form. It's not a quadratic equation. So we can factor. Or try to factor. If it didn't factor, you can still use the quadratic formula. If you find it difficult or more challenging to factor with the trig functions listed in the equation, make a substitution. Now come over here to your scratch paper and make it 3u squared plus 2u minus 5 and figure out how that factors. You can factor it however it is that you like to factor your trinomials. For me, I like trial and error. So I would have 3u and u, and I would try 1 and 5 or 5 and 1. And it turns out that it works if we put a 5 here and a 1 here, with a plus on the 5 and a minus on the 1. So here I was over on my scratch paper, but now let's substitute that information back over here. So we have 3 cotangent of x plus 5 times cotangent of x minus 1 equals 0. So if we set each of our factors equal to 0, we would have cotangent of x equals negative 5/3, and cotangent of x equals positive 1. I prefer to write it with respect to the tangent because I'm going to use my calculator here in a minute. So tangent of x equals negative 3/5, and the tangent of x equals 1. Now, when you're looking at these, do pay attention as to whether it's something you're expected to know without your calculator. This one should look familiar to you. And we know that the reference angle for this one is pi over 4, so I shouldn't need my calculator for that. For this one, that isn't one of my special angles or a quadrantal angle here, so I would grab my calculator and punch in inverse tangent, and I always use the positive ratio, so the reference angle will pop out right away. So the inverse tangent of 3/5 is approximately equal to, I'm being very casual here when I wrote equals, we know it's approximately equal to 0.54. Let me just double check that. Inverse tangent of 3/5. Yeah, 0.54. So now we throw those reference angles into the appropriate quadrants. We know the tangent is negative in the second and fourth quadrants. So if we put 0.54 in the second quadrant, we have pi minus 0.54. That would be 2.60. And if we put it, let's see, in the fourth quadrant, we'd have 2 pi minus 0.54. And we would have 5.74. All right, that's putting this reference angle into the second and fourth quadrants. And you could come over here in your scratch paper, draw yourself a picture. It looks like this. Here was the pi minus 0.54, and over here in the fourth quadrant, it is 2 pi minus this 0.54, and that's where these numbers come from. Similarly, for this one, pi over 4 is not just a reference angle, it's also one of the solutions, because we know tangent is positive in the first quadrant and also in the third. So when we throw pi over 4 as a reference angle into the third quadrant, we have 5 pi over 4. So we have these two exact solutions and these two decimal approximations to our solutions for this particular equation. Let's do one more. Let's see. Let's let it be this. We're going to find the solutions between 0 and 2 pi again, but here's the equation. 6 cosine 2x plus 11 sine x minus 6 equals 0. And notice here we have a double angle and then just the sine of x. So I hope this brings to mind your sign of the double angle identities. You know you have 3 of them that you should know. That the cosine of 2x equals cosine squared x minus sine squared x. We know it's equal to the cosine of 2x is equal to 2 cosine squared x minus 1. And it's also equal to 1 minus 2 sine squared x. So anytime I see the cosine of the double angle, I'm considering whether making a substitution with one of these would be appropriate. And certainly with this equation, I see this sine x here. I'm looking at this as my substitution. So I'm going to replace this cosine of 2x with this equation right here. And by the way, you could make it work if you made one of these substitutions instead, but you would then have to make a further substitution. So this would get us there most directly. So 1 minus 2 sine squared x, there's my substitution. And now I don't have a double angle anymore. Plus 11 sine x minus 6 equals 0. Let's distribute the 6. So we have 6 minus 12 sine squared x plus 11 sine x minus 6 equals 0. Oh, look, our 6's cancel. So we have negative 12 sine squared x plus 11 sine x equals 0. Now I'm going to multiply both sides by negative 1 just because I don't like the leading coefficient, I like it to be negative. But you don't have to do this, but I prefer to, so I'm going to. So I'd have 12 sine squared x minus 11 sine x equals 0. Starting to look better. Notice this is factorable if we factor out the sine of x. And then we'd have 12 sine of x minus 11 as our second factor. We can set each of these equal to 0. So we have the sine of x equals 0. And we have 12 sine of x minus 11 equals 0. So for this equation, we know that the sine of x is equal to 11/12. Again, we always look to see if these are equations that we should just know the solutions to. And I hope you see it right here. This is one of our quadrantal angles that we should be seeing here. We know the sine of x is equal to 0 at 0, pi, 2 pi, 3 pi, 4 pi, and so on. But the numbers that are between 0 and 2 pi are 0 and pi. And I'm not even including 2 pi. Notice it's excluded from the interval here. Now for this one, this isn't one we recognize. So let's find the reference angle. So we punch in inverse sine of 11/12. And we get 1.16. Since we're looking for solutions in the first and second quadrants because of the positive ratio, not only is 1.16 a reference angle, it is also one of the solutions. So 1.16 is a first quadrant solution, and we need our second quadrant solution, so we have pi minus 1.16, so that we would be in our second quadrant, and you'll have 1.98 as your second solution. So I hope that gives you a good idea on how to solve a variety of trig equations, and now go practice some yourself.